Hi, I'm Derek. I'm excited to share our work DICE Data Efficient Clinical Event Extraction with Generative Models from UCLA Computer Science. Given a clinical node, clinical event extraction aims to extract occurrences at specific points in time during a clinical process, as well as its arguments, which are textual entities that modify or describe properties of these events. Given this example sentence, we could extract two events shown in the two tables. The first event is an sign-symptom event triggered by nodule with three arguments about detailed description, area, and biological structure, while the second event is triggered by computed tomography. Automatic extraction of clinical events can help downstream tasks such as automated clinical decision support, adverse medical event detection, and drug discovery. However, there are several non-trivial challenges of clinical event extraction compared to general domain event extraction. First, most triggers and arguments of clinical events consist of domain-specific terms that are more than 50% longer than the general domain on average and have vague boundaries because most clinical mentions contain several descriptors. For instance, given the tag span massive heart attack should be identified as the trigger instead of massive heart attack or attack only, because it refers to a specific condition, and massive is an argument of the road type severity. However, when we consider right common carotid artery, the entire text span describes a biological structure. The second challenge is the diversity and density of clinical arguments. There are on average 2.5 times unique argument rows for each clinical event type compared to the general domain. Finally, it's challenging to obtain high-quality annotated data for clinical events due to both patient privacy concerns and the cost of expert annotations. Our methods handle these challenges by introducing an event extraction model specializing in mention identification through contrastive learning, accelerated learning, and mention boundary markers. And our model performs independent queries for each argument row to better handle long-tail argument rows. We further introduced the first clinical event extraction dataset with argument information to address the data availability issue. We repurpose an existing expert annotated dataset Macrobet, which has 200 English clinical case reports from PubMed and partial event annotation. We incorporate all entities, event triggers, event types, and definition sentences into the new Macrobet EE dataset, and we additionally introduce argument-related information by inferring arguments via the modified relation. Macrobet EE is the first clinical event extraction dataset with argument annotation. When we compare the statistics with widely used general domain event extraction dataset, we observe there are 2.6 times potential argument rows per event type. The events in sentences are 2.3 times dense, and entities in Macrobet EE is almost 1.7 times long. For methods, we formulate the event extraction task as a conditional generation task with 3 sequence-to-sequence components. The mention identification task aims to extract candidate trigger or argument mentions with a sliding window. The event detection component aims to extract event triggers and predict event types. And the event argument extraction extracts event arguments and predicts row type. To handle long-tail potential arguments, we perform independent query for each argument row. We further propose techniques to enhance the generative model's ability to accurately identify long mentions with vague boundaries. First, with a contrastive learning strategy. For each output target, we create multiple negative targets. Each negative targets have some perturbations on the correct mention boundary to include few wrong additional tokens or remove few unnecessary tokens. Distinguishing the subtle boundary difference are not specifically optimized during pre-training or fine-tuning. We create such a task and train the model specifically to recognize the mention with the correct boundaries from a pool of mentions with similar but shifted boundaries. We use an influenza loss to learn to identify the positive target from a pool of candidate target with mention boundary perturbation. We also wrap case bands with special token markers to hint the model about explicit boundary of mention candidates. And we further perform joint training of the mention identification tasks and the event tasks to learn implicit synergistic training signals for the subsequent extraction capability needed for all 3 components. When using all training data to train, we observe DICE outperforms baselines in all 4 tasks. And the low resource setting, compared with the best baseline, DICE achieves more than 8 points F1 score improvement when using 10% training data for argument classification. DICE especially shows its superiority in low data setting. We study the effectiveness of the mentioned enhancing techniques, and we observe all 3 mentioned enhancing techniques are helpful. Combined, that leads to more than 5 and 3 points F1 score improvements for trigger and argument classification, respectively. If we further break down the error cases in the 4 subtasks in the entire Evenix reaction pipeline, we observe that mentioned identification enhancement techniques leads to fewer error cases in all identification error types in both trigger and argument identification steps. Thank you for watching. We are excited to share our code and data at derek.ma/dice.